Today I'm going to show you some techniques on how to simplify radicals. And we're in section 3.3, which is page 3 of your chapter 3 notes. So to simplify a radical, you go through a two-step process. First of all, the radicand, which you remember hopefully that's underneath the radical sign, you express the radicand as the product, which means multiplication, of factors. So we're going to have to try to split this radicand up if we can. First of all, any perfect squares are going to be first, and then followed by things that are not perfect squares. Or if there's a perfect cube, we'll do that, and I'll tell you what that's all about. After you get this radicand split up into factors, then you're going to take the square root or the cubed root of all of the perfect squares, perfect cubes from part A. And then after you take the square root, that's called the coefficient of the radical, and that'll go out front. And then what you don't take the square root of, it's left underneath as the radicand of the answer. So those are the two steps, and we'll go through a bunch of examples to show you what that means. But first of all, you should be very familiar with this list of perfect squares: 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Whenever you see a number on this list, it should automatically ring a bell that these are the perfect squares. So if you just see a 121, automatically you should say, oh, that's 11 squared. Or a 25, oh, that's 5 squared. And another list of numbers you should know are the perfect cubes: 2 to the third, 3 to the third, 4 to the third, 5 to the third, 6 to the third. 7 and 8 and 9 to the third are not really as important, these three numbers, but you should know that 10 to the third is 1,000. So at least these first 4 numbers on this list and 1,000, you should recognize those automatically as being perfect cubes. And then other powers you should know. You should know 2 to the 4th. Remember, 2 times 2 times 2 times 2. So you have 2, 4, 8, 16. 2 to the 4th is 16. 3 to the 4th. 3 times 3 is 9. Times 3 is 27. Times 3 is 81. So 3 to the 4th is really 3 squared times 3 squared, which is 9 times 9, which is 81. And if 2 to the 4th is 16, 2 to the 5th is just 2 times 16, which is 32. And 2 to the 6th is 32 times 2, which is 64. So those are some other numbers that you should be recognizing as perfects. So now what we're going to do is we're going to go through these next 6 examples to simplify these radicals. The first one is the square root of 50. So you can recognize, hopefully, that there's a factor in 50 that's on this list of perfect squares, and that would be 25. So you're going to write the 25 first. 25 times 2, remember it's the product. So we're going to split 50 up into its perfect square times what comes next. After you get done with the perfect square, I would like you to circle the perfect square. Sometimes there are going to be multiple perfect squares when we get into variables underneath. And then that perfect square, you pull that out, take the square root of 25 and call it 5, and he goes out of the radical as a coefficient, and then the 2 stays underneath. So whatever's not circled stays under, whatever is circled comes out front. 700. 700 has a factor that's on this list of perfect squares, and that's 100. So you're going to rewrite that as 700 is 100. 100 times 7. You're going to circle the 100 because that's the perfect square. Take the square root of 100, which is 10. And then what gets left underneath is what you don't circle, which is a 7. 72 is one of those tricky numbers. 72 has multiple factors on this list of perfect squares. 4 goes into 72. 9 goes into 72. The biggest number that goes on into 72 on this list, though, is 36. You're going to pick the largest number from this list of perfect squares that goes into this number right here, 72. So 72 we're going to break up. 72 is the square root of 36 times 2. So that's the first thing we're going to do, is break the 72 up. The next thing we come to is an x. X is not a perfect square, so we're just going to put it as an x. Y to the 4th. Anytime you have an exponent that's even, that's a perfect square. So we're going to just leave that as y to the 4th. We're going to circle the 36 because that's a perfect square. We're going to circle y to the 4th because that's a perfect square. And then we're going to take the square root of each one. The square root of 36 is 6. The square root of y to the 4th is y to the 2nd. Remember, you divide that exponent in 2. And then what stays underneath? What we didn't circle, which was the 2 and the x. So that's how you simplify that one. The next one is the square root of 32, x to the 5th. It's a little sharper here. Now 32 is another one of those numbers that has more than one perfect square in it, because 4 is in 32, but the biggest number that goes into 32, the biggest number on this list of perfect squares, is 16. So we're going to break 32 up into 16 times 2. Now x to the 5th is not a perfect square, but we can break that up. We can call that x to the 4th times x to the 1st. So whenever you have an odd number as an exponent, break it up into the next smaller number times x to the 1st. And then we're going to circle the 16 because it's a perfect square, and circle x to the 4th because that's a perfect square, and bring those two out front by taking the square root. The square root of 16 is 4. The square root of x to the 4th is x to the 2nd, and what we didn't circle stays underneath as a 2 and an x. And that one is done. The next thing we have is a cubed root. You see the little 3 in the index. That means a cubed root. So we're going to break this apart. Now 512 is on that list of perfect cubes up there. So 2 cubed, 3 cubed, 4 cubed, 5, 6, 7, 8 cubed is 512. And you can check that on your calculator if you want. 8 to the 3rd is 512. So negative 512, the cubed root would be negative 8. But x to the 5th we have to split up. So we'll call that negative 512. It doesn't have to be split, but x to the 5th splits up into, whoops, we have to put a little 3 in that index. Whoops. You have to put a 3 in that index, and x to the 5th splits up into x to the 3rd. Now what we have to do is have this exponent be a multiple of this index. X to the 3rd times x to the 2nd will give you x to the 5th, and that's how you break apart x to the 5th. Remember, the first thing you write here will be a multiple of that index. So we're going to take the cubed root of negative 512. We're going to take the cubed root of x to the 3rd and bring them out front. Cubed root of negative 512 is negative 8. The cubed root of x to the 3rd is x to the 1st. And then what stays underneath the cubed root? The x squared. The last thing we have is a fraction, and this is the 4th root. Well, the 4th root of 16 is 2, because 2 to the 4th is 16. So remember, you can take a 4th root of 16 and get the 2 back again. The 4th root of 81 is 3, because 3 to the 4th is 81. So if you take the inverse, which is the 4th root of 81, you're going to get a 3 back again. And then we have an x to the 5th, which is not a multiple of 4, so we're going to have to break that apart. But y to the 16th is a multiple of 4, so we're going to keep that. So what we can do is rewrite this as the 4th root of 16 times x to the 4th times x, and on the bottom 81 stays and y to the 16th stays. So the perfect fourths, 16, x to the 4th, 81, y to the 16th. Everything gets circled because we're going to take the 4th root, and then everything comes out front. 4th root of 16 is 2. The 4th root of x to the 4th is x to the 1st. On the bottom, the 4th root of 81 is 3, and the 4th root of y to the 16th, remember you divide 16 by 4, 16 divided by 4 is 4. So this is y to the 4th, and what do you have left? You have the 4th root of what we didn't circle, which was just an x. And you can put it as a fraction, or you can just leave it like that. So that's simplifying. A simplified radical cannot have a fraction underneath the radical. Also, the denominator may not contain a radical. So what we have in these examples is we have fractions under here that we're going to have to do something called rationalize the denominator. It means that when the radicand is a fraction, like 2/3 or 5x over 6y, what we're going to have to do is get rid of this fraction. And to do this, we're going to multiply the numerator and the denominator by the same number, which will make the denominator into a perfect square or a perfect cube, whatever we're taking the root of. And then we're going to take the root of that, and then after that multiplication, we're going to get a perfect square in the denominator, so there won't be a fraction underneath anymore. What I mean by that is if you have the square root of 2/3, you're going to look at the denominator, and since it's not a perfect square, we're going to make it into a perfect square. We're going to multiply 2/3 by 3 over 3. Well, what's 3 over 3 anyways? It's just 1. So we're going to multiply 2/3 times 1 to keep it equal to itself. And look what happens. 2/3 times 3/3 is equivalent to 6/9. So if you take the square root of 6/9, well, look at that. We have 9 as a perfect square. We're going to take the square root of 9 and get 3. And the square root of 6 over 9 is just the square root of 6 over the square root of 9. And the square root of 9 is 3. So this is called rationalizing the denominator, because you're not supposed to have a radical in the denominator, and you're not supposed to have a fraction underneath the radical. So this would be, it would be called a simplified radical, because that's what we're doing. Remember, we are simplifying radicals. And in this case right here, we just have to get rid of that fraction. In this example, we have a 5x over 6y, and 6 is not a perfect square, neither is y. So we're going to create a perfect square in the denominator by multiplying the top and bottom by 6y. So if we multiply the top and bottom by, remember, 6y over 6y equals 1. So if we multiply 5x over 6y by 1, which is in the form of 6y over 6y, 5 times 6 is 30. X times y is xy. 6 times 6 is 36, and y times y is y squared. So what we have now is a perfect square, 36, and perfect square y squared, which we're going to take the square root of 36 and get 6, the square root of y squared and get y. And what we have on the top is just the square root of 30xy, because we can't simplify that radical at all. So now we've gotten rid of the radical in the denominator. Rationalizing the denominator. Here's another example which is just a little bit different. We have a 7x to the 5th over 5y to the 7th. 7 and 5 are not perfect squares. X to the 5th and y to the 7th, that can be reduced, but what we're going to do is to get this denominator to be a perfect square, if we multiply 5 times 5, we'll get 25. If we multiply y to the 7th times y to the 1st, we'll get y to the 8th. And y to the 8th is a perfect square, and that's what our goal is to get that denominator to be a perfect square. So here's the original problem, 7x to the 5th over 5y to the 7th. If you multiply by 5y over 5y, which is just equal to 1, remember, what we get in the top is 7 times 5, 35, x to the 5th, times y, and in the bottom 5 times 5 is 25, y to the 7th times y to the 1st, add those exponents, 7 plus 1 is 8, and now in the bottom we have a perfect square. We have 25, which is a perfect square, which we're going to take the square root of and get 5, and we have y to the 8th, which is a perfect square, so we're going to take the square root of that and get y to the 4th. So we have, and the other thing we can do is we can break x to the 5th down into, and I didn't show this step, but x to the 5th can be broken down into x to the 4th times x. So when you take the square root of x to the 4th, you get x to the 2nd. Take that square root and get that x to the 2nd. And so the 35 stays underneath, the x to the 1st stays underneath, and so does the y. Couple other examples down here at the bottom. 9 is already a perfect square, so we don't have to multiply it by a number to get that up to a perfect square. But a to the third is not a perfect square, so we're going to have to multiply that by a to get it to be a perfect square. So let's multiply. First of all, we have the given 10 over 9a cubed. And if we multiply the top and bottom by a, what we're going to get is on the top 10a, and on the bottom 9a to the fourth. Well, 10a can't be simplified, so we're going to take the square root of 10a and leave it on the top, but on the bottom we're going to take the square root of 9 and get 3. We're going to take the square root of a to the fourth, and the square root of a to the fourth is a to the second. So that would be that one simplified. In the second example, number 8, we have a 3 as a coefficient. That just stays outside. We have a similar example. We have a 9, which is a perfect square already. And what I'm going to do is I'm just going to take this equal sign. I'm going to just change that to multiplication and extend that to save some writing. I'm going to multiply this by b over b, because b to the 7th times b to the 1st will give you b to the 8th, which will be a perfect square. So on the outside we have a 3. We have 5a to the 7th b over 9b to the 8th. And we can take the square root of 9 and b to the 8th and get, I'm hurrying myself here. The 3 stays on the outside. This 3 is that 3. The square root of 5a to the 7th b on the top. And on the bottom, take the square root of 9 and get 3. Take the square root of b to the 8th and get b to the 4th. And now we have some more simplifying we can do. We can cancel these 3's because they're factors. Sorry for that noise outside. I've just covered up this mistake that I've made. Hopefully you've written in pencil so you can erase it. I'm sorry, I wrote it in pen. Well, what we're down to is canceling out those 3's, and we're left with a 5a to the 7th b as a radicand. And what we can do is we can split that a to the 7th up into, so I'm going to take this numerator, rewrite the 5. A to the 7th is really a to the 6th times a to the 1st, and b is not a perfect square. And on the bottom, outside of the radical, we just had a b to the 4th because the 3's canceled. Well, this a to the 6th is a perfect square, and what we're going to do is move that outside, take the square root of it, and get a to the 3rd. So the final answer of this one is equal to a to the 3rd on the outside. On the inside of this radical, you have a 5 and an a and a b that I haven't circled, and then on the denominator we have a b to the 4th, which is not in the radical. So that is the final simplified answer for number 8. And then going on to number 9. Number 9 is the trickiest one of all because this is a cubed root. And what we have to do is we have to go up to our perfect cubes and see which one of these perfect cubes goes into 16. Well, the only one that'll go in will be an 8. So we're going to split up 16 into 8 times 2. Another thing we have to do is we have to get rid of this y to the 5th because it's in the denominator. And we have to move this 5 up. We have to make this 5 equal to some multiple of 3. Well, if we multiply the top and bottom by y, so I'm going to just extend this out and multiply the top and bottom by y. So this will become a y to the 6 in the bottom. So we'll take the cubed root of 16. 16, like I said, can be broken up into its perfect cube, which is 8 times 2. That's 16. Now let's take this x to the 4th. X to the 4th can be broken up into a perfect cube of x cubed times x to the 1st. That'll give you the x to the 4th. And then remember we tacked on a y. In the denominator, we have a y to the 5th times a y to the 1st, which is y to the 6th. And then the last step we're going to take is we're going to take the cubed root of all perfect cubes. So circle the 8, that's a perfect cube. Circle the x to the 3rd, that's a perfect cube. Circle y to the 6th, that's a perfect cube. And we're going to bring them all out to the front. The cubed root of 8 is equal to 2. The cubed root of x cubed is equal to x. Then we're going to have a cubed root of what we didn't circle, which is a 2 and an x and a y. And in the denominator, there's no radical because we're not supposed to write one there. The cubed root of y to the 6th, 6 divided by 3 is 2. So we have a y to the 2nd in the denominator. So this one, number 9, is completely simplified when you've got it down to this answer right here. And that's the end of my video today. Have a great night.